Throughout the entirety of human history, our species has been defined by a single, driving obsession. We are obsessed with value. We fight devastating generational wars for sticky black oil buried deep beneath the burning sands. We dig boreholes miles into the crust of our own planet, risking lives and toiling in the suffocating darkness just to extract veins of gold. We have built our entire civilization on the concept of scarcity, the idea that because something is rare, it must be precious. On our little blue marble, resources are finite, and we scrap for every ounce, measuring our nation's worth by their reserves and their vaults. We scrape the earth, sifting through tons of rock and dirt to find small, sparkling fragments of pressurized carbon we call diamonds. They are the ultimate symbol of wealth, of power, and of everlasting commitment. We adorn our crowns, our scepters, and our engagement rings with them, believing them to be the absolute pinnacle of luxury. But what if I told you that Earth is poor? What if I told you that our entire global economy, every bank, every stock exchange, every vault in Fort Knox, and every billionaire's portfolio combined, is nothing more than a rounding error compared to what lies out there in the dark? 41 light-years away from where you sit right now, within the faint, crab-shaped constellation of Cancer, there is a star named Copernicus. To the naked eye, it is invisible, lost in the vastness of the night sky, indistinguishable from the void. But orbiting that star is a world that defies the laws of imagination. It is a world that, by all conventional logic, shouldn't exist. It is a super-Earth, a planetary titan twice the width of our home and 8 times as heavy, a dense ball of matter that challenges our understanding of planetary formation and survival. But it is not the size or the weight that has captivated astronomers and dreamers alike for 2 decades. It is the composition. Imagine a planet where the bedrock isn't granite, limestone, or basalt, but graphite and diamond. A world where the interior pressure is so immense and the carbon so abundant that a massive percentage of the planet's mass, perhaps a third of it, is believed to be pure crystalline diamond. This is 55 Cancri A, also known as Janssen. If you were to appraise this planet using Earth's current market value for diamonds, the price tag is estimated at $26.9 nonillion. That is a 26, followed by 30 zeros. To put that incomprehensible number into perspective, if you gave every single human being on Earth $1 trillion and did that every day for a year, you wouldn't even scratch the surface of this planet's worth. It is a cosmic bank vault that makes the total combined wealth of human history look like pocket change found in a couch cushion. But we must ask ourselves, is this cosmic jewel box truly a paradise of riches? Is it a treasure waiting to be claimed by some future miner? Or is it something else entirely? As we have peeled back the layers of this distant world with our most advanced telescopes, from the heat-seeking eyes of Spitzer to the optical clarity of Hubble, and now, the infrared mastery of the James Webb Space Telescope, we have discovered that beauty often hides a terrifying reality. Today, we are taking a deep journey across the galaxy. We will explore the physics of a diamond world, the hellish conditions of its surface, and the groundbreaking new data that suggests this diamond might actually be sweating lava. This is the story of the most valuable and perhaps the most dangerous real estate in the universe. To truly understand the planet, we must first understand its master. The context of any world begins with its sun, for the star dictates the destiny of its planets. The story begins 41 light-years away. In cosmic terms, This is right next door, practically in our backyard. The light from this system takes only 4 decades to reach us, meaning the light we see tonight left that star when the first space shuttles were flying. On a clear winter night, if you know exactly where to look in the northern hemisphere sky, scanning the darkness between the constellations of Gemini and Leo, you can almost see its host star with a standard pair of binoculars. This star is 55 Cancri A, officially named Copernicus. Copernicus is a G-type star, very similar to our own Sun. It has roughly the same mass, the same temperature, and the same familiar yellow-white glow. If you were floating in space near it, looking out a viewport, it would feel eerily familiar, perhaps even comforting, like looking at a mirror image of our own solar home. However, Copernicus is older than our Sun, richer in heavy elements, a cosmic elder that has seen more of the galaxy's history. And it is not alone. It is part of a binary system. Far in the distance, over 1,000 times the distance from the Earth to the Sun, a small, dim red dwarf star orbits it, acting as a silent, red-hued sentinel, watching over the system from the freezing dark. But our focus is on the primary star, because Copernicus is a very busy parent. It hosts not 1, not 2, but 5 confirmed planets. When astronomers first started detecting these worlds in the late 90s and early 2000s, it was a revelation. It was one of the first multi-planet systems we ever found, providing the first concrete proof that our solar system wasn't a fluke, that crowded families of planets are actually common in the galaxy. However, the innermost child of this family, the one closest to the fire, is the strange one. 55 Cancri E was discovered in 2004. At first, we didn't see it directly. We found it by watching the star wobble. As the planet orbits, its gravity tugs on the star, causing the massive Sun to move slightly back and forth. This is called the radial velocity method, a technique that allows us to feel the ghost of a planet without ever seeing its face. It requires incredibly precise measurements, detecting shifts in light as small as a walking pace. The data derived from this wobble was shocking. This planet was incredibly fast. It completes a full orbit around its star in less than 18 hours. Let that sink in for a moment. A year on Earth is 365 leisurely days, marked by the slow changing of seasons. A year on 55 Cancri A is 18 hours. It takes less time for this planet to complete a year than it takes for a plane to fly from New York to Singapore. In the time it takes you to watch a few episodes of your favorite show, an entire calendar year has passed on this world. If you lived there, you would celebrate a birthday every single day, aging thousands of years in a human lifetime. It hugs its star at a distance of just 1.5 million miles. For comparison, Mercury, the scorched inner planet of our solar system, sits 36 million miles from the Sun. 55 Cancri A is practically skimming the surface of the nuclear fire, dipping into the stellar corona, dancing on the razor's edge of destruction. At this proximity, the gravitational forces are immense. The radiation is blinding, and the heat. The heat is unlike anything we have ever seen on a rocky world. It creates an environment so extreme that it pushes the very definition of planet to its breaking point, existing in a state of matter that is alien to everything we know on Earth. So why do we think it's made of diamond? Why not just hot rock, like a larger version of Mercury or a melted Mars? The answer lies in the chemistry of the star itself. In astronomy, there is a golden rule: you are what you eat. Planets form from the accretion disk, the same disk of primordial dust and gas that creates their host star. If we analyze the light from the star using spectroscopy, breaking the light down into a rainbow to see the chemical fingerprints hidden within, we can figure out what the planets are likely made of. Our Sun is an oxygen-rich star. Because of this, Earth is an oxygen-rich planet. Our rocks are silicates, compounds of silicon and oxygen. That's why we have sand, granite, and quartz. The ratio of carbon to oxygen in our solar system is low, about 1 to 2. We are a silicate world living in a silicate neighborhood, built on a foundation of oxygen bonds. But in 2010, researchers took a closer look at the spectrum of 55 Cancri A. They found something peculiar. This star appeared to be unusually rich in carbon. The initial studies suggested that the carbon-to-oxygen ratio was much higher than our Sun's, perhaps even greater than 1. This completely changes the recipe for planet building. It's like trying to bake a cake, but replacing all the flour with sugar. The result is going to be something unrecognizable. In a carbon-rich environment, oxygen gets used up quickly to form water or carbon monoxide, leaving a massive surplus of carbon behind. As the planet 55 Cancri A began to form billions of years ago, condensing out of the solar nebula, it wouldn't have coalesced from silicate dust like Earth. It would have formed from carbon dust, graphite, and carbides. In 2012, a team at Yale University ran the geological models based on this data. They published a paper that sent shockwaves through the press and the scientific community. The model suggested that 55 Cancri A was composed primarily of carbon in different allotropes. Picture the structure of Earth: a thin crust, a rocky mantle, and an iron core. Now picture 55 Cancri A. The crust would be dark graphite, the same soft gray material found in your pencil lead, perhaps miles thick. But as you dig down, the pressure increases exponentially. Carbon is unique. Squeeze it hard enough, and the atoms rearrange themselves. The opaque, slippery graphite bonds shatter and reform into a rigid crystal lattice structure. The model predicted that a huge portion of the planet's mantle, a layer thousands of miles thick, could be pure diamond. We aren't talking about small gems embedded in kimberlite rock like we find in South Africa mines. We are talking about a continuous, solid shell of diamond, a planetary layer that would be practically indestructible, a global gemstone. Beneath that, a core of molten iron and carbides. It was a hypothesis that captured the world's imagination, a planet made of money. However, science is never static. As we would later learn, the Diamond Planet nickname might be technically true deep underground, but on the surface, the reality is far more volatile and far less inviting than a jewelry store. The dream of the diamond world was about to collide with the reality of a lava world. Let's descend from orbit. What would it actually be like to stand on the surface of 55 Cancri A? First, you would feel heavy, crushing weight. This is a super-Earth. The gravity here is roughly twice as strong as what you are used to. If you weigh 150 pounds on Earth, you would weigh 300 pounds here. Every step would be a struggle, like carrying another person on your back constantly. Your bones would ache under the strain, and your heart would have to work double time just to pump blood to your brain. But the gravity is the least of your worries. Because the planet is so close to its star, it is tidally locked. This is a gravitational phenomenon we see throughout the cosmos. Just as our moon always shows the same face to Earth, 55 Cancri E always shows the same face to its sun. One hemisphere is trapped in eternal, blinding daylight. The other is frozen in everlasting night. There is no sunrise. There is no sunset. The sun simply hangs there forever, a fixed, burning eye in the sky. The difference between these two sides is absolute. On the day side, the star Copernicus dominates the sky, huge and terrifying. It spans 1/60th of the sky, dozens of times larger than the sun looks from Earth. It doesn't just shine, it roars with radiation. The temperature on this substellar point, the point directly under the star, climbs to over 2,400 degrees Celsius, which is about 4,400 degrees Fahrenheit. To put that in perspective, lava from a Hawaiian volcano is about 1,200 degrees Celsius. The day side of 55 Cancri A is more than double the temperature of fresh lava. It is hot enough to melt iron, titanium, and even vaporize rock. It is a heat that destroys molecular bonds, a furnace that tears atoms apart before they can even form complex structures. If the diamond theory holds, the surface graphite wouldn't just be hot, it would be liquid. Or perhaps it would be gone entirely, stripped away to reveal a bubbling, glistening ocean of liquid carbon and carbides. Now, imagine walking towards the horizon, towards the terminator line, the twilight zone where day turns to night. This boundary ring was once thought to be the only potentially habitable strip on the planet, a place of eternal dusk where the temperatures might be survivable, bathed in a perpetual sunset. As you cross into the night side, the star disappears. Darkness takes over. For a long time, scientists thought the night side would be freezing cold. Without a thick atmosphere to carry the heat around, the dark side should be near absolute zero, a frozen wasteland of carbon ice where nothing moves. But when the Spitzer Space Telescope mapped the planet's heat signature, it found something strange. The night side wasn't freezing. It was still hot, scorching in fact, over 2,000 degrees Fahrenheit. How is this possible? How does heat travel from the day side to the dark side on a planet made of rock? On our moon, the dark side gets incredibly cold because rock is a bad conductor of heat. The thermal anomaly on 55 Cancri E was the first clue that something more dynamic was happening. The answer led to one of the biggest debates in astrophysics, the atmosphere question. For 10 years, 55 Cancri E played a frustrating game of hide-and-seek with our telescopes. Every time we looked at it, the data seemed to change, contradicting the previous findings and confusing astronomers. In 2016, Hubble detected hydrogen and helium. Scientists thought, maybe it's a gas dwarf like a mini Neptune. But the radiation from the star is so intense that light gases like hydrogen should have been blown away into space billions of years ago. Physics said it was impossible for a small planet to hold on to such light gases so close to a star. They would evaporate like mist in a desert. Then, another study suggested the planet was completely bald, a bare rock with no atmosphere at all, like a giant molten Mercury, stripped naked by stellar winds. But the heat map from Spitzer didn't lie. Something was moving the heat around. If the planet was just bare rock, the hottest point should be directly under the sun at high noon. But the hottest point was shifted. It was offset to the east. Think about a hot summer day on Earth. The hottest part of the day isn't noon when the sun is highest. It's usually around 3 p.m. Why? Because the atmosphere takes time to heat up and the winds move that air around. The offset hotspot on 55 Cancri A proved there was circulation. There was wind. And if there is wind, there must be air. But what kind of air exists at 4,000 degrees Fahrenheit? This isn't oxygen or nitrogen like we breathe. In this hellscape, the atmosphere would likely be made of vaporized rock, silicates, and perhaps cyanide. Yes, cyanide. If the carbon-rich theory is correct, the chemistry of the atmosphere would be deadly. We are picturing clouds made of exotic mineral vapors, rain made of liquid lava falling from a sky that might be yellow, sepia, or choked with black soot. It is a toxic soup that would kill a human in seconds. Yet it is the lifeblood of this planetary weather system. It is a witch's brew of chemistry that we barely understand. The leading theory became a secondary atmosphere. The idea is that the original atmosphere was stripped away by the star long ago, but the planet is geologically active. Volcanoes, thousands of them, are constantly erupting, spewing gas from the molten interior back into the sky, replenishing the atmosphere faster than the star can blow it away. It is a constant battle between the planet and the star. A cycle of destruction and creation happening every second. The planet is literally sweating gas to protect itself. But we needed proof. We needed a telescope powerful enough to chemically taste the air of a world 41 light-years away. We needed to see the invisible spectrum. We needed the James Webb. Enter the James Webb Space Telescope. Launched in 2021, JWST is the most advanced piece of technology humanity has ever put into the void. With its massive gold-plated mirrors and highly sensitive infrared sensors, it can see the chemical signatures of worlds light-years away. In 2024, humanity pointed this mechanical eye at 55 Cancri A. The astronomical community held its breath. This was the moment of truth. JWST observed the planet as it passed behind its star, an event called a secondary eclipse. By measuring the thermal emission, the heat glow, before and during the eclipse, the telescope could subtract the star's light and tell us exactly what the atmosphere was made of. It was like trying to spot a firefly next to a spotlight. But JWST was up to the task. The results were groundbreaking. JWST ruled out the lava world with no atmosphere theory. It detected a clear, strong signal of carbon dioxide, CO2, and carbon monoxide, CO. Now this might sound boring. It's just car exhaust, right? Wrong. This was a monumental discovery. This was the first time we had detected a substantial atmosphere around a rocky super-Earth outside our solar system. It proved that a planet can keep a gas shell even while hugging a star this tightly. It defied the pessimistic models that said the star would strip it bare. But the data revealed something even more fascinating about the surface. The data suggests that 55 Cancri E is indeed covered in a magma ocean. But this magma is bubbling. The CO2 and CO are likely outgassing from this global ocean of liquid rock. So let's update our mental image. Forget the static, glittering diamond field for a moment. Picture a world where the ocean is made of molten carbon and basalt. The water is glowing red and orange lava, viscous and churning. The air is a toxic mix of carbon dioxide and carbon monoxide, thick and heavy, creating a hyperactive greenhouse effect that traps the heat and distributes it to the night side. And floating on top of this magma ocean, perhaps rafts of solid graphite like icebergs made of pencil lead, clashing and melting in the heat. It is a scene reminiscent of the early Earth, the Hadean Eon, but chemically alien. And deep below that churning, liquid surface, that is where the diamond treasure likely remains. The pressure deep in the mantle is still enough to keep the carbon crystallized. The diamond core is safe, wrapped in a blanket of liquid fire, inaccessible to any drill, any ship, or any human hand. So we return to the question of value. 26.9 Nonillion. It is a number that exposes the absurdity of human economics. It highlights a paradox. Value is scarcity. Value is defined by what we cannot easily have. If we could build a ship large enough to travel the 41 light-years, a journey that would take hundreds of thousands of years with current technology, and if we could somehow mine the planet without melting our machines, what would actually happen? If you brought even a fraction of that diamond back to Earth, say a single cargo ship full, the global market would crash instantly. The supply would flood the demand. Diamonds are valuable because they are rare here. On 55 Cancri A, diamond is as common as dirt. To a hypothetical alien living in that system, a piece of wood, a breath of oxygen, or a drop of liquid water would be infinitely more valuable than a diamond the size of the Titanic. The true value of 55 Cancri A isn't in its potential for jewelry. It's in its potential for knowledge. For a long time, we searched for Earth 2.0. We looked for planets that mirrored our own, hoping to find a backup home. But 55 Cancri E teaches us that the universe is far more creative and far more diverse than that. It shows us that planets can form in chemical environments totally different from ours. It opens the door to carbon worlds, a whole new class of planets where the rules of geology, and perhaps even biology, are completely rewritten. It challenges us to think beyond our silicon-based bias. Could life exist there? Almost certainly not on the surface. It is a sterilizing hell. But the discovery of complex atmospheres on rocky worlds brings us one step closer to finding a world that does have the right ingredients. It proves that rocky worlds are resilient, that they can hold on to their skies against the odds. As we look up at the night sky, at the faint stars of the Cancer constellation, it changes your perspective on the universe. We used to think of planets as simple categories: rocks, gas balls, or ice chunks. Now we know there are worlds made of gemstones. There are worlds that rain glass. There are worlds darker than coal and hotter than stars. We are just beginning to scratch the surface of the strange variety the cosmos has to offer. 55 Cancri A, the diamond planet, is a reminder of nature's excess. It is a world of extreme beauty and extreme terror, locked in a gravitational dance that will last for billions of years. It sits there, 41 light-years away, a $26 nonillion treasure chest that no hand will ever touch. And perhaps that is for the best. Some jewels are meant to be admired only from afar, safe in the velvet display case of the cosmos, burning brightly in the dark. Thank you for joining me on this deep dive into one of the cosmos's most fascinating anomalies. If you enjoyed this journey, be sure to subscribe and hit that bell icon. The universe is vast, and we have many more strange worlds to explore together. Until next time, keep looking up.